Today we are going to do a logistic regression, just a brief review of this algorithm and where do we use this algorithm, along with some brief mathematics but not in deep. Then we'll try to apply it on iris dataset, which is a good famous dataset to practice on. Okay, so what is logistic regression? So last time we learned about the linear regression. Now the name may confuse you. The regression part mainly is used to predict a continuous value, but here logistic regression is used for the classification task. So let's have an example. What might be the classification task would be? Task would look like, okay, importing numpy. Let's just create a synthetic data first. Let's classify this data as if the data is greater than 3 or not. So false, 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 true, true. So that's mean that 4 and 5 is classified as true because it is greater than 3. Let's just plot the data. Let me take one more. So it's a data point from 0 to 100, and we have classified it such that the number is less than 50 or not. So this is some of its synthetic data, right? Or maybe we could classify also it like if it is divisible by 3 or not. We don't know. It's just a synthetic data. So look at the shape of this data. Basically, this data is divided by an imaginary line. All right. We cannot look at the y direction because it is the probability, is the prediction. That should be the prediction. We are only given the number 0 to 100. So it's basically a point at this x line which is dividing these two categories. So now how do we approach this task? So we got what logistic regression suggests is we're gonna predict 1 for the true label and 0 for the false label. For the logistic regression, in previous lecture, like in linear regression, we used to have a loss function and we used to have a function. At that time, in linear regression, it was just a straight line function which is equal to y equal to mx, which was giving us the required regression prediction subjected to that particular loss function, which was mean square error. In here, the function that is used to predict 0 and 1 to classify the data is sigmoid function. So this is the formula for sigmoid function. Let's just look at it. So this is sigmoid function. So what it suggests, um, if x is from minus infinity to infinity, the sigmoid function tends to 0 as x approaches to negative infinity, and it tends to approach 1 when x tends to infinity. At 0.5, at x equal to 0, it tends to point 0.5. Now what do we want is to, so here is the formula is 1 upon 1 plus e to the power minus x. So now how can we use this function? So let's say x is our input feature which is given to us. What do we want? We want to extract information from it. The information could be of any type, so we gonna multiply it with some coefficients m1, m2, m3, which are also called weights, and at last we will add some bias. So our our main motive is to learn these parameters m1, m2, m3 and bias in such a way that for this class which is greater than 50, or the true class, the sigmoid function tends to 1. That is, if 1 upon 1 plus e, we're not passing x here, we are passing mx, that is multiplying by the weights and adding the bias, which is also z. We call z is mx, or the m1 into x1 plus m3 by multiplying by weights and evaluating them. So 1 upon 1 plus e to the power minus z here. So we want z to be such that for true category it tends to be at 1, and for false category it tends to go to 0. So this is the main idea about using the sigmoid function. And this picture also looks like something like the sigmoid function. Okay, so the aim is pretty clear here. We need to find these parameter m1, m2, m3 and bias in such a way that when the input features are multiplied by these weights and then pass through a sigmoid function p, the value of the true labels should come out to be nearly 1 and the false label should come out to be nearly 0. Okay, so we need to subject this function, this aim, to a loss function which calculates if the true label tends to go to 1 or not, or the false label tends to go to 0 or not. So the loss function that we use for this motive is cross entropy. So how do we come up with this function? So let's see this. So the loss log function, we want that for true labels, answer should be as uh, near to 1 as possible, right? So if it is near to 1, the loss should be 0. If it is equal to 1, then the loss should be equal to 0. So we can just have log of the probability, log of the value of p, which is come out after evaluating the sigmoid function, right? So this sigmoid function, the value of p, if the label is true, then p should be near to 1. All right, then p should be near to 1. So what's log p? It should be near to log of 1. So this is half the part. Now what if the label is 1, label is 0? That is false. We need that p should be near to 0. So we can simply say that log 1 minus p would become log 1, which comes out to be 0, right? But what if p is near 0? Then log of p would become log of 0, which is very large. the loss increases. Similarly here. So this concept tends to work very good with this. So here we need to combine these two, right? So we want if the label is 1, then we should implement this loss. So if label that is label, let's say label y represents our label and p is the prediction label. Prediction, right? So we want loss such that if the label y is 1, then loss would be log into p. Alright. But what if the label is 0? Then y is 0, so this term becomes 0. Alright. But if the label is 0, then we can say 1 minus y into log of 1 minus p as discussed here. So this comes out to be the our loss function. Alright. So let's look at the graph of log. You know that the value of log between the range 0 and 1, it's negative, right? So, and the prediction that we are getting, the value of p is also between 0 and 1. So that's mean the value of log would be negative always. So to counter this, make a negative sign in front of it. So that's how we get a loss function here. All right, so this is a loss function. So basically we are just uh, using 0 to 1 part of the loss log function to get a loss function. So let's say when the loss, now if we multiply it by minus like we did here, if we multiply it by a negative sign like we did here, so we'll get this as opposite. It will start from here and go from here. We'll just reflect the graph around the axis. Okay, so the value of um, when the label is 1, when the label is 1, the loss function, our cross entropy loss function would look like this. If the variable, if the p value is near to 0, it would tends to infinity, right? But if it is um but if it is near to 1, the loss would be 0. All right, so this is I've written here. So cross entropy loss is basically the same loss that we've discussed so far. Now why here represent one data point? Like here we have 100 data points, we are given 100 data points, so we're gonna uh, evaluate it for every data point, this function, and then add the loss function, add all the losses to get the final loss function. Now this is the loss function. So basically now what is our aim? Our aim is to find the value of weights and bias in such a way that our loss is minimized. So a quick recap, we are given x, which is a data point. It could have many features, x1, x2, x3, x4, so many things. We are multiplying it with some weights and adding some bias, and then we are passing it through a sigmoid function to get a prediction value which can be ranged from 0 to 1, right? Now, to get these weights attain their optimum value, we are subjecting this condition to a loss function, and this loss function is cross entropy loss. Now, we need to minimize this loss function with respect to the values of m1, m2, m3, so that um, we can approach we can start with so we can apply the minimization algorithm. All right. So anyone have any doubts? They can ask. Mm, okay, so let's coming to the next part. So subject how do we find this value subject to that minimum, that loss function? We're gonna find the derivative. So we have variables like m1, m1, m2, m3, and so on, and a bias, right? So we're gonna find the derivative of the loss function with respect to these variables. All right. For every variable, then we're gonna apply the minimization algorithm, which suggests that after finding to find the optimum value of the weight with the loss function, there's always a graph which gives you the optimum value. So, as discussed earlier in the linear regression, we use the algorithm which suggests that m1 should be m1 minus learning rate into the gradient. And we do it iteratively so that we can find the optimum value of m1. So the learning process is basically same for the linear regression and logistic regression. The thing that differs is the sigmoid function that we are applying on top of this manipulation, and the loss function, which is cross entropy. Okay, so yeah, so the sigmoid function is e to the power minus mx. Wait, let me confirm it. Yeah, it is negative. So basically P of z could be written as this exponential z. Z is equal to mx as I told you earlier. Then 1 upon 1 plus e to the power minus z. So minus z would be 1 upon e to the power z, and we get this after simplification. So we can write this part as this, and we can apply chain rule to differentiate it. The final result p dash z would be pz into 1 minus p of z. Now this is not the derivative that we need. We need, this is the derivative with respect to z. We need to find the derivative with respect to every weight m1, m2, m3. So we're going to differentiate it further with respect to m1, m2, and m3. You can look into Wikipedia to get a deep of the mathematics. Now coming to the practical part. So how we going to apply it? Okay. So let's just, there's a data set called iris data set. Let me, let's just read the description of it. Characteristics, number of instances 150 हमारे पास data points हैं. There are 150 data points, out of which there are 3 classes, and each class have 50 data points. So one data point consists of 4 numeric um, features that we need to work on, and a prediction class. All right. So attributes हैं sepal length, sepal width, petal length, and petal width. In the class, so basically Aries is a flower something, and Iris is a plant, which have these 3 types of classification, and these classification from observations are dependent upon these features, these 4 things, or maybe more, but these 4 things are enough to classify these values into these these classes. Okay, yeah, so that's it. So this is the overview of the data set. So let's just view the values. So these are the 4 features. All right, iris.data. These are all the values of these data points. Okay. So 150 total data. The mean is around 5.8 for the 0th characteristic. 3 here, 3 here, and 1 here. So this just gives the analytics about the data. That mean that for like in business activity, it can be used in something else, like for shares or something. It can be used. The main could be useful to find the average share, although and standard that how's the data is varying. All these are basically used for the statistics part. Okay. Hmm. So here are the targets 0, 1, and 2. So let's just divide the dataset into training and test for training and testing purposes. So let's say train X, test X, test Y. Okay, so we have uh, the the um, labels here. Now for now we only need to import the logistic regression module and leave these values to the algorithm and let it train. So to uh, have the module, we can use the sklearn library from sklearn linear model. It is a linear model. Why is it a linear model? Because here we can separate the two classes by a single line. If the classes is basically in concentric circles, let's say the class is, here is a class, a zero is a class, and then outer zero is a class, then it is very difficult to simply just use this algorithm to classify that, because it's classified on the basis of a line, because it is a linear model. We can also classify the nonlinear by using some of the techniques, by introducing nonlinear features, which I talked about, like cross featuring uh, that we discussed in the last class. All right. Import, let's say, logistic regression. So a model, make a class of logistic regression, and we're gonna with model dot fit train x and train y. So these are the values of the model. Now here we have c is equal to 1.2. This is a use for a, this will be discussed in next class. This will be our next topic. What is the value? What is the significance of c? Basically, you can say it is used in a loss function. What we do, we add the weights of these. We want that m1, m2, m3 and all these bias should have a minimum value as possible. Okay, they should have minimum value possible. So we add the absolute values of these, or squares value of these, and add it to the loss function alongside our information. Like, I'll add the mod of all these values with the cross entropy function, like plus करके here. Plus sum of weights. Now, so the loss function is now basically a combination of these two. Now we need which to what to give more importance to, right? We need that, we want to give more importance, that we should get right answer. So for that purpose, we multiply it by c. If c is like 5, so we'll give 5 times the importance to this loss as compared to this loss. So we'll discuss it in detail in the next class. Okay, so we were We have the model trained here, and so we need to test how it's work. So we have a the mean accuracy. It says our model is 97% of time, 97% accuracy. So how can we improve this accuracy? Maybe we have all these numerical values. What if we just divide these values into a discrete values, like uh, find out the range of 0, find out the range of minimum is 4 and max is 7.9. Okay, and minimum is 2, max is 4.4, minimum is 1, 6.9, 0.1, 2.5. Maybe divide these values into ranges and then mapping those values into ranges like discrete values a b c d, so that it may not have to differ for 3.31 and 3.30. You can also work like that, or you can also apply cross featuring. That's one way to do. So yeah, there it is, 97%. So this was whole logistic regression idea. So in simple terms, it is basically an algorithm which is used to classify, uh, for classification purposes. We have some features. We have some features x1, x2, x3, and x4. Here we have four features: 0, 1, 2, 3, and we need to find m1, m2, m3, m4, and a bias. We need to find in such a way that the loss is minimized. And the loss function that we use is cross entropy. And then we use a minimization algorithm. It's as simple as linear regression, but the thing is, our aim is different, our loss function is different, and the way of finding the prediction is different. Okay, so that's it.